How many degrees of freedom does your mouse have? I'm guessing all it measures is 2, just movement along 2 axes. But your mouse is also free to rotate. Unfortunately, mouse hardware isn't set up to actually capture rotation data. Most modern mice have optical sensors, which are tiny infrared cameras that scan the surface of your mousepad. This is great for measuring motion, but the area the sensor covers is too small to accurately measure rotation. So how can we measure rotation? Well, the most obvious answer is using a gyroscope, which directly measures rotation. However, for this use case, it's possible to achieve a better quality result by sticking with optical sensors. We know that one sensor isn't going to cut it, but if we had 2 sensors spaced apart, and the sensors detect movement in opposite directions, then we can infer the rotation. So I picked up 2 PMW3389 sensors made by PixArt, which seems to be the largest supplier of gaming mouse sensors. And these things have some pretty insane specs. They have like 16,000 CPI, which should be more than enough for this project. Next I need a microcontroller. I chose the Blue Micro 840 because it's small, has a floating point unit, and wireless capabilities. Because after all, you wouldn't want a wire getting in the way when you do a SICK 360 with your mouse. Last, I needed a sacrificial mouse, so I picked up a cheap one for only $15. The one that I chose happened to be a rebranded Glorious Model O. So the first step was to open the donor mouse and remove all the junk that wasn't needed. We won't need the USB cable or most of the circuit board, although we will need the portion that has the switches and the scroll wheel. Also, the sensor opening needs to be cut away to make room for the second sensor, so I cut away this hexagonal part on the bottom. Next, I decided on a component layout. I placed the sensors side by side and the battery at the back with the microcontroller on top. And with this plan, I modeled a frame to hold the components, and then it was off to 3D printing and assembling the frame. And a test fit, it looks like the fitment is good. Next, I wanted to make some progress on the software side of things, so I began on a prototype board by hooking up the MCU to a sensor. There's a library for another PixArt sensor called the PMW3360, which I forked and modified to work on the PMW3389. The most important changes are the firmware image and 2 registers for setting the CPI. Once all the issues were fixed, I was able to get some basic movement data out of the sensor, and with this I felt confident with soldering wires onto the MCU and assembling the mouse so I could continue developing the firmware. The next step was to add the wireless functionality. There's a library called Bluefruit52lib, which makes it pretty easy to create Bluetooth devices. I got a basic Bluetooth mouse working, but it had an issue where if you moved the mouse too fast, the cursor would move in the opposite direction. This happens because the sensor data is 16-bit, but the mouse report is only 8-bit. Unfortunately, the fix is a bit more complex. I had to discard the library-provided HID mouse solution that I was using so that I could supply my own HID descriptor and report with the 16-bit values. And after doing this, there were no more issues with the cursor moving in the wrong direction. The next issue was the polling rate. I was only getting about 30 Hz, which made mouse movement extremely choppy. After some debugging, I discovered that the mouse was stalling waiting for a transmission queue to empty before sending the next transmission. The problem is that the default transmission queue size is 1. But fortunately the queue size is easily configurable, so I increased it to 32. But this doesn't completely solve the problem. This would send 32 notifications all at once, then stall, then send another 32 notifications all at once. The fix for this is to add a small artificial delay between the notifications to prevent the queue from filling. The moral of the story is that sometimes you need to go slower to go faster. And with this change, I finally had buttery smooth mouse movement. So to recap, I started with the mouse, then removed the mouse part, and then added back the mouse part. So that means it's time for the whole point of the project, which is rotation. And it's literally just this one line. That's the whole thing. Well, let me explain. We have 2 sensors that are some fixed distance apart, and then we receive data from them. The movement is obtained by averaging the data from the two sensors. And to calculate rotation, we undo the movement. And now the sensors are symmetrical about the origin, so we just ignore the one on the left. And now we can create a triangle, and we see that the angle is just the arctangent of y over x. And this is the angular movement of the mouse. Finally, it's time to make use of the data. I thought it would be funny if the cursor rotated, so that's where I started. For this, I modified a compositor called Weston. And with the compositor, programs are first rendered into off-screen buffers, and then the compositor pieces all of the buffers together into the screen image. This means we can apply transformations to the buffer before it's shown on screen, transformations such as rotation. The cursor is a separate buffer as well, so we just need to hook up the rotation data from the mouse to the cursor transformation. The Weston codebase is fortunately very clean, so this task was pretty easy. And anyway, here it is. Now this is useful. But it would be even more useful if you could rotate windows. So I applied a similar transformation to windows when moving them, and this was the result. Surprisingly, everything just works. You can even click and interact with the windows, and even menu creation works. If you can rotate windows, then that opens up the possibility for a new kind of 360 no-scope. Traditionally, these are done in the transverse plane, but we are uniquely positioned to achieve the world's first 360 no-scope in the coronal plane. It may have been against a bot, and I may have cheated by increasing the rotation sensitivity to 1/8 of a turn for a full 360, but there it is. In all seriousness, what are the practical applications of this? Well, an obvious one is rotating things in Photoshop or rotating maps, but perhaps this has an application in competitive gaming. Not by using rotation, but by correcting for rotation. Consider this. You need to hit a headshot, so you use your muscle memory to move the mouse and click, and it lands. But let's say you're gripping your mouse slightly differently, and your mouse is rotated by like 1 degree. The same movement will result in a different aim, which may be the difference between a headshot and a miss. In this demonstration, I'm correcting for rotation. You can see that no matter how I move the mouse, even if it's upside down, left moves the cursor left and right moves the cursor right. Compare that to a regular mouse. You also get the benefit of a lower liftoff distance, since data is only sent if both sensors are contacting the table. So that's it, at least until I make a version 2. And if for some reason you want to make this project for yourself, I've uploaded the code for the firmware, the fork of Weston, and the step files for the mouse frame on GitHub. The links are in the description.